Hello everybody, I am Subrata Roy, research scholar, Coachbihar Panjab University. I would like to thank the organizer to give the opportunity for this presentation of our work. Today in International Conference on Nonlinear Dynamics and Applications, I am showing a short presentation about our work. The title of the talk is Cylindrical and Spherical Ionoacoustic Shock and Solitary Waves in a Non-Planar Hybrid Q-Non-Extensive Non-Thermal Plasma. Investigation on plasma environment becomes an interesting topic in recent times as it is ubiquitously found in space environments as well as laboratory experiments. The observations made by Viking spacecraft and Freezer satellite showed the importance of electrostatic solitary structures. Shokdev observed theoretically this type of waves by considering mechanical analogy, whereas EKG in the year 1970 studied the same with an experimental setup. Subsequently, several authors paid their attention to observe the various types of plasma models. Sometimes the physical plasma environment becomes finite and the waves are confined to move in a bounded state. Such type of non-planar geometrical space arises in capsule implosions, supernova explosions, Saturn's magnetosphere, etc. Further, several authors performed their theoretical and experimental works to observe the behavior of ionoacoustic wave in different non-planar plasma systems. Recently, Demire observed the ionoacoustic wave propagating in a non-planar plasma system comprising positively charged cold ions and electrons satisfying hybrid Q-non-extensive non-thermal velocity distribution. Some experimental on-plasma circumstances indicates that the characteristic of wave propagation in a dissipative system significantly depends on interparticle collisions and viscosity, etc. To consider the impact from viscosity, a Barger term is added to Demire's observation, which may produce solitary as well as shock type wave features. For negligible values of dissipation term, solitary type wave features produces and shock type wave produces in the presence of strong dissipation. Outline of our work is we investigate the propagating properties of ionoacoustic wave in a plasma comprising positively charged ions and electrons abiding by hybrid Q-non-extensive non-thermal velocity distribution equation. Considering the impact from the ion streaming velocity, interparticle collisions and viscosity, a Barger's term is introduced in the present system. The non-planar Korteweg de Vries Barger's in short form NKDV equation is derived from the basic governing equation. Using weighted residual method, simplified Hiro-Linear method, progressive solitary wave solution and shock wave are derived. Finally, the effect of different physical parameters on solitary and shock wave on the propagation of ionoacoustic wave in the present system is noticed. So, the main problem formulation is the dynamics of the system is described by normalized basic governing equations 1a to 1c. Here the parameter mu equal to 1 and 2 signifies the motion of cylindrical and spherical ionoacoustic waves, whereas the dynamics of planar ionoacoustic wave is represented by mu equal to 0. In this model equation, n denotes the normalized number density of cold ion, u represents the velocity of ion fluid, the electrostatic potential is noticed by psi, delta is the viscosity coefficient, a density of normalized Q non-extensive non-thermal electron is given by Ne, where the parameter alpha determines the non-thermal electrons number in the system. In the extensive limiting case, when Q tends to 1 and alpha equal to 0, this distribution reduced to a Maxwell-Boltzmann velocity distribution, and when alpha not equal to 0, this model or distribution function reduced to Crane's distribution. To derive the NKDV equation, the standard RPT method will be utilized. In order to derive the depending variable n, u and psi are stated as a series form. Now using the state coordinate xi, tau and damping in the viscous plasma parameter delta, we get the equation non-planar KDV Barger equation. Here P denotes the nonlinear coefficient, depends on the parameter alpha and q. The solitary wave type becomes compressive when p greater than 0, whereas it becomes effective for p less than 0. To detect a suitable parametric domain, the variation of the nonlinear coefficient p and the dispersion coefficient q due to the change in the parameter alpha and q are shown in this figure. Now, the analytical solution for non-planar KDV equation. Here we apply the weighted residual method to obtain the approximate analytical solution for NKDV equation. In order to employ the weighted residual method, we utilize the solution of the standard KDV equation. So using the solution 9, finally we obtain the solution of non-planar KDV equation, which is given in equation 11. This analytical solution can be reduced to planar solution when mu equal to 0. This figure exhibits the variation of amplitude in planar and non-planar wave profiles, and it is found that the planar wave moves over the cylindrical wave and spherical wave. These two figures show the evolution of cylindrical and spherical wave respectively for different time intervals. The significant impact of the Barja's term follows from this figure. Enhancing delta 0 causes for losing of potential energy of the system, and naturally the solution have negligible backward shifting with declining amplitude. The impacts of non-extensive parameter q on the wave propagation are depicted in figure W. It is found that the wave gets steepened with enhancing alpha and gets flattened due to the rise in non-thermal electron numbers. For a clear vision of wave propagation, the three-dimensional profiles of the cylindrical and spherical wave are drawn here. The significant impact of Barja's term in diminishing amplitude is also understood from the figure O. These are the corresponding contour plots of the 3D figures. Now, the analytical shock solution of the non-planar KDV equation derived by simplified Hirota bilinear method. The solution is of the form 14. This figure exhibits the evolution of king type solution for different times in cylindrical geometry. From this figure it is clear that the increasing delta 0 leads the solution to move deeper. The significant effect of non-extensive parameter q is shown in this figure. It is important to note that there is a critical point of the parameter q for which anti-king type shock are found below the values of critical point, and oppositely king type shocks exist for higher values of q. These are the 3D plots of the 2D figure. Now we conclude our results. Using basic governing equation in the propagation of cylindrical and spherical ionistic wave in magnetized plasma comprising positively charged cold ions and electrons describing hybrid q non-extensive non-thermal velocity distribution are analyzed through the NKDV model. The weighted residual method and simplified Hirota bilinear method are employed to obtain a new class of solitary and swag wave solution for the present system. The significant effects of different physical parameters such as alpha, q, delta 0 and time parameter t are observed from the numerical standpoint. Finally, it can be concluded that the results of our investigation may be helpful to observe the propagating behavior of solitary and swag waves in laboratory plasma as well as space plasma environment. Due to the fixed time duration, details calculation omitted here. For further details, respective listeners are requested to see the manuscript. These are the references. Thank you, everybody.